Analysis and balancing the one-part model cell. Now that you have eliminated waste and streamlined your cell, you are ready to assure yourself that you have the needed capacity and have balanced the work among your cell operators. In this tutorial, you will learn how to compensate for any operations that exceed takt time and prohibit you from meeting your production goals. You will also learn how to combine work steps to minimize the operator resource required to complete the part within takt time. We will utilize a graphical technique called the takt time cycle time chart to map the operations and visualize how they relate to takt time. We will use this same chart to aid us in combining operations and determining the number of operators required in the process. Remember takt time? In a previous tutorial, you learned how to calculate takt time. You learned that the takt time is the beat of the cell and is established by both the demand and time available for production. To learn the capacity analysis and balancing techniques, we will first explore a simple one-part model cell. Later, in a second tutorial, Capacity Analysis and Balancing, Part B, Multiple Model Part Cell, we will utilize the techniques learned in this one-part model cell tutorial to determine capacity and balance a cell that has multiple part models. Capacity Analysis, the one-part family cell. After you have eliminated the waste you observed in your cell and operators are comfortable with the new process, complete a new set of trial timings using the cycle time analysis sheet. This sheet requires 5 observations of each operation and will provide us with the average of these observations and a 98% time. The 98% time accounts for operator and process variations and means that 98% of the time we will be able to complete the operation within this time. Using the 98% time from the cycle time analysis sheet, let's build our takt time cycle chart for a one model cell. The takt time cycle time chart provides a graphical picture of how each operation fits in relation to the takt time. Along the horizontal axis, sequentially list each operation name. In our case, shear, punch and break, weld adapter, and so on. The height of the y-axis needs to be tall enough to cover the time it takes to complete the longest operation that you observed. In our case, we observed operation 40, weld sides complete, to take 55.1 minutes. Starting with the first operation, add a bar for each task until you have plotted the entire part process. The bar for each operation should be drawn so that both automated and manual time are stacked as seen here in operation 70 and operation 80. Put the color-coded manual time on the bottom and stack the automated portion of the operation on top. This will make balancing steps easier to visualize. Now calculate the takt time. The takt time is simply the time available for production divided by the demand for the product. In our case, after calculating the total shift time and subtracting time for breaks and meetings and allowing for 90% capacity, we have 216,000 minutes times 90% or 194,400 minutes available for work. The demand for the product is 4,000 units. So in this case, the takt time is 194,400 minutes divided by 4,000, or 48.6 minutes. Draw a horizontal line across the cycle time chart at the takt time value of 48.6 minutes, and label it. The resulting graph is the takt time cycle time chart, and gives you a visual representation of each of your operations compared to takt time. Take note of which operations are above and below the takt time. Operations below the takt time are easily completed without constraining the cell. However, those above the takt time represent constraints to meeting customer demand and need to be addressed. Let's look at the constraint for this cell. The bar that extends above the takt time in operation 40, weld sides complete, and see how to bring it below the takt time. Bringing operations within takt time. If you have a task that exceeds takt time, there are several ways to break this constraint. The preferred method depends on whether the constraining operation is manual or automated and should consider the cost of implementing the solution. What to do if a manual process exceeds takt time? If you have a manual task that can be split into smaller pieces, consider having multiple operators work on the part simultaneously. If 2 or more operators can work simultaneously on the same part, or can process half the part and pass it to the second operator, consider having multiple operators work the part. This will result in breaking the operation into 2 parts and bringing each bar below takt time. thus breaking our constraint. In our case, we added a second welder and a piece of whip so that one operator can work on a part and pass it to the other welder. If you have a manual task that cannot be split into smaller pieces, or only one operator can work on the part at a time, consider adding a piece of inventory, or work in process, to the cell, and having two welders, each performing the full operation. While neither welder will be able to complete one part within the takt time, together they will be able to complete two parts in two takt times, thus putting sufficient parts into the line to allow one part to move to the next operation during each takt time. What to do if the automated process exceeds takt time? Sometimes you will find an automated operation exceeding takt time. When this happens, you have several options to break the constraint. 1. Study the automated cycle. Can you reduce the cycle time by eliminating some wasted motions? Can you speed up the traverse motions to bring the automated task under takt time? If you can eliminate enough waste, you can break the constraint. 2. If the process is capable of processing multiple parts automatically, look at batching parts so that the automated cycle is, say, 2 times the takt time. Use 2 parts and complete 2 parts in 2 takt times. By processing 2 parts at a time, you will have one for the next operation for each takt time, and the batch process will feed the buffer to the next operation. While this requires some extra inventory in the cell, most cells start out with so much inventory, and with Lean offering huge improvements in inventory reduction, keeping a few well-placed parts is not an issue. If you can process multiple parts within multiple takt time, you can buffer the next operation and break the constraint. Overtime. Can you work this process extra hours each day? Can you add a partial shift to this automated process? If you can work this operator overtime, you can break the constraint. This option will add some whip to the process. This should be weighed against other options. 4. If reducing waste and adding overtime does not solve the problem, can you obtain another piece of equipment to add capacity? Remember, the piece of equipment you require does not need to be the best and the fastest. It only needs to provide sufficient capacity to bring the process within takt time. If you can obtain another piece of equipment, you can break the constraint. This option does add a few pieces of whip. Be sure to evaluate the cost of whip and the cost of adding the equipment. Balancing. Now that each task can be completed under the takt time, we will balance the resources required to produce the part. For each operation that is below the takt time, look to see how it can be combined with other operations below the takt time. Ideally, we should bring the total work content of each operator to takt time. This would be the ideal number of operators. To find the ideal number of operators required for the work in the cell, add all the manual times to complete the process and divide by the takt time. This number is equal to the ideal number of operators required in the cell. If this calculation results in fractions of operators, you can either work on waste reduction or process improvements until you can get to the next lowest full number of operators. Alternatively, you can round up and have a partial resource available to float in the cell and help other operators, or resupply consumables to the cell. In our case, we have a total manual time of 128.1 minutes and a takt time of 48.6 minutes. Dividing, we get 2.6 operators required. Since 6/10 of an operator is closer to 1 than to 0, we would round up and require 3 operators in this one model cell. When you are combining tasks to fully utilize the operators, combine like skill sets, and consider the cell layout to combine operations so that each operator has a combination of tasks to do that will come complete in a time equal to or under takt time. It is important to consider the skill required for the task. In this case, to break the constraint, we have broken the weld sides operation into segments so that multiple welders work on the part. You can see for operator 1, the sum of the 98% times for shear, punch and break, weld adapter, and weld sides is 20 plus 15 plus 10 plus 3.6 minutes, for a total of 48.6 minutes of work, our takt time exactly. The second operator welds for 48.6 minutes on the weld sides operation, again, our takt time exactly. The third operator does the final tasks of weld sides for 2.9 minutes, then completes the operations of weld baffle, test, clean and dry, paint, assembly, and package. Sounds like a lot, but it is a total of 31.6 minutes of labor. easily completed under our takt time of 48.6 minutes. This operator has some open time before the next part arrives. He would be responsible for unloading the automated operations, assisting the other two operators if they need a hand, and he can supply the cell with its consumables during his open time. You will notice that we've added 2 pieces of WIP to the third operator's area. These enable the operator to complete each operation and then continue processing a part. Without these pieces of WIP, he would be idle until the automated cycle is completed, and a part becomes available for him to process. Summary. Congratulations! You have now learned how to balance your first one-part model lean cell. You have learned how to identify constraints using the takt time cycle time chart. You have learned techniques to compensate for both manual and automated operations that exceed takt time and prohibit you from meeting your production goals. You have learned and utilized a graphical technique, the takt time cycle time chart, to map the operations and visualize how they relate to takt time. And you have learned to balance a cell by combining like operations and moving towards the ideal number of operators required to complete the part. In the next tutorial, we will learn how these same techniques allow us to determine capacity and balancing a tougher, more realistic problem, a cell that contains multiple part models with varying cycle times and demand quantities.